Swayam Prabha. Digital India. Educated India.
We'll start where we left off last time. So, we were talking about this Smolichevsky equation, right, and we started with the diffusion controlled reactions. So, just a brief recap. If you have to estimate the upper limit of the second order rate constant between solid molecules in solution, then one would use this diffusion control theory developed by Smolichevsky, right. Then the primary condition under this is that for any reaction to occur, the solid molecules will have to diffuse to the solvent and then collide or encounter, because if they do not collide or encounter, obviously no reaction is going to happen, and we are talking about a bimolecular reaction. Again, according to Arrhenius theory, not every encounter will lead to a successful collision. Successful collision, I mean that a successful reaction is going to happen, right. Now, because it is just not a collision, after collision you have to cross an activation barrier. Okay. So, the encounter rate therefore determines the upper limit of the second order rate constant, assuming activation energy to be 0. That means, what it assumes is once you have a collision, you are going to have a reaction, that was the assumption. So, for derivation what we did was we started with Fick's second law, right, and then we moved ahead and derived, and during derivation we came to this. This was this I of A, this I was referred to as a current, right. So, it's sort of a collision current, and it has a negative sign. Remember, the negative sign is there because if you have a particle like this, then the diffusing particles would be moving towards, because if this is increasing distance from the particle is actually moving towards. Why they are moving towards? Because they have a concentration gradient, right. So, that is why that is what the negative is, and we define this K of A. So, this K of A, let us see. So, this K of A is something we defined, which is the diffusion controlled rate constant, which is equal to 4 pi d times A, where d is the diffusion coefficient and A is the radius of the sphere that we were assuming. Now, then we also said at the end of the class that for two diffusing phase A and B, if both of these have reasonable radii and also they have their own diffusion coefficients, then the collision current can be expressed as this, where we are talking about relative motion, and in relative motion the speeds get summed up. So, in this case also we are doing the same thing. The d is equal to d of A plus d of B. R0 is A of A plus A of B, that is the radius of sphere A plus the radius of sphere B. And remember, in this case we are talking about hard spheres, right. That means they cannot push or push them inside, and then you have K R0, which is 4 pi dA plus dB times R0, and again this collision current also depends upon the concentration of A and the concentration of B in solution, Ca naught and Cb naught, right. So, this was your I of A. So, just something about units, because if you would look at some standard textbook, then you would come across something like this. So, for example, if I am going to have this collision current, right, then let us say that is A, which is the radius, is in meters, and some meters, right, 10 to the minus 9, 10 to the minus 8, whatever. Then the diffusion coefficient is meter square over second, okay, that is the unit, and C0 obviously is the concentration, it is in molecules per meter cubed. But generally when we talk about a system, what do we consider is we do not consider molecules, we essentially consider what moles, right, that is what we do. So, we have to make the transformation, And also remember, in general form, when we are talking about concentration, we do not express it in terms of moles per meter cube. What do we do is we express in terms of moles per liter. Okay. So, you have two transformations, one is from molecules to moles, which will include what? Multiplication by a certain constant, which is the Avogadro's number n of A, right, or n. The second is, if it is molecules per liter, or rather moles per liter, if you have to go for moles per meter cube, then what would happen? Multiplied by 10 to the power 3, right, because 1000 liters gives you 1 meter cube. Okay. So, that is essentially what you will see out here. To express concentration in moles per meter cube, now it is moles per meter cube, not moles per liter, we can write 10 to the power 3, which is the liter to meter cube conversion, right, times n. What is n? The Avogadro number times I of A gives you the equation, right. So, you are just multiplying 1000 n with I of A, right. Then K of A becomes 4 pi d times A times 1000 or 10 to the power 3 times n. Okay. So, if you would take any standard textbook, this is possibly one of the ways you would be seeing this K of A represented, right. So, but do not get confused, I mean if you really stick to units, this is what you would be coming across, and you just kind of figured out why you would be having that factor of n and that factor of 10 to the power 3, right, clear. So, now, so that is then finally it becomes the most general form, where K of R 0 is 4 pi f R 0, I will tell you what f is, times dA plus dB times 10 to the power 3 times n. Now, what is f? We will not go into much of details with regards to f, but this is what f is. F is a certain factor, f is a certain factor which is different from diffusion. See, this is something which we are considering, what based on what we are considering only diffusion, right. Now, suppose you are talking about two charged species. If two charged species are coming close to each other, right, or even any non-charged species, when they would come close to each other, they cannot come very close to each other. What will happen? You would be having Van der Waals forces, Van der Waals forces coming in, or if there are two charged species, what would you would be having Coulombic forces coming in, right. So, think about this now, it is not only the diffusion, then these factors also start creeping in to your actual rate constant. So, that is why what you do is they just include another factor f, as I said, we will not be going into too much of details, or as such no details with regards to that, with regards to f, but if there would be another factor f, that would essentially decrease the reaction rate. Okay. So, that is what f is, any factor which is other than diffusion, that is what it means. So, in general, if you would consider a diffusion controlled reaction, what you would do is you would take f to be what? 1. Okay. That means everything else is assumed to be not important, the only thing which is going to be determining my actual rate is the diffusion. Okay. So, this in a nutshell is what diffusion control theory of rate reaction is, developed by Smoluchowski, and there are many variants of this. If you would ever be interested, just look into it, it is very interesting. Okay. So, this is just a numerical example, taking some numbers to give an idea. Say again we take f is equal to 1, we take r naught to be 2 times 10 to the minus 9, 10 to the minus 9 is nanometers, right, that is 2 nanometers. Then d of A, which is for a small molecule, is 5 times 10 to the minus 10 meter squared second inverse. D of B is for a protein, say it is a interaction between a protein and a ligand, something like that. Then you can see that K of R 0 comes to be 8.3 times 10 to the minus 9 mole inverse second inverse. Now, this is huge. You can understand, right, what rate constant means, 10 to the minus 9, this is huge. Now, what does it mean? What it means is that you cannot have a reaction which is faster than this, right, because this is diffusion control only, there is no other factor absolutely, and because it is diffusion control, this is the fastest rate at which the reaction can happen. Okay, this is your, that is why it is called, it is your diffusion limit. Now, if you, for people who have heard about fluorescence, or for people who work on fluorescence, you would know there would be something known as quenching, fluorescence quenching. So, how does fluorescence quenching happen? If you have a fluorophore, right, say your sphere, and then if you have quenches, any quenching molecule, say does not matter what the quenches are right now. So, these quenches would be diffusing, then the fastest rate of quenching would be happening, or you would be having is based on your diffusion control, and hence when you go ahead and derive fluorescence quenching equations, you would see they just take help of this theory. and that is one of the very important things, because quenching is so widespread in use in fluorescence or people who deal with fluorescence. Okay. So, that is one practical application of this diffusion control theory. And these are some diffusion constants, just to have more ideas, like say diffusion of water, it is 10⁻⁵ centimeter square per second, this centimeter square. So, meter square you can easily do it. Then diffusion of alcohol in water. Now, look at diffusion of lipids in the membrane. So, diffusion of lipids in the membrane, it is called a fluid phase. Fluid phase means where the lipids are fluidic, right. It is 10⁻⁷ centimeter square per second of lipids in a membrane. Gel phase, you know what gel phase happens. In gel phase, it is kind of more rigid, that is what gels are, right. Like any, you take any like polyacrylamide gel or any gel, the difference in a gel and a fluid is in gel you kind of have a mesh like network, diffusion is restricted. In fluid, diffusion is obviously fluidic, more free, and hence you can see the difference in diffusion constant. And diffusion of proteins in a membrane, 10⁻⁹ centimeter squares per second. Now, guys, the last value is extremely important, and now you have to appreciate this, because we have cell membranes, right. A lot of our reactions do happen in cell membranes, right. You have to have diffusion inside cell membranes. So, essentially then diffusion, apart from other things, is what, depending or banking on this diffusion constant. It is diffusion over specific protein. Okay. So, diffusion is very important, just get it from me. I mean, whatever you consider, whatever you see, whatever you look at, diffusion would be involved in some way or the other. Okay. So, we move on to another very important equation. This is known as the Langevin equation. Now, what Langevin said was very simple. What he said was this: suppose I have a spherical molecule or just a molecule inside a solvent, and the molecule is bigger than my solvent molecules, right. So, what he said was, consider a large particle of mass m immersed in solvent molecules, right. So, this is typical schematic. You can see you have mass m in the middle, and then you have these small solvent molecules. Now, what you can see, one thing is, now appreciate this or realize this, if you have a solvent, if you have a big mass m in a solvent molecule, small molecules, then what will happen? They would always, or the solvent molecules will always collide with this, but also remember that this collision would be random in nature. You look at the directions, you look at these arrows, right. You look at these arrows, you look at this arrow, you look at this arrow, see there is no specific direction, right, and you would not expect it to be, because you have thermal energy, thermal fluctuation. These molecules do not have any solvent molecules have any specific gradients, so they just collide and collide randomly. And because we are talking about random collision, what motion are we talking about now? We are talking about Brownian motion. So, this is what Brownian motion results from, okay, random collision. So, you can understand then there would be a randomly colliding force, right, a certain force. Okay. Now, next is, as I said, solvent molecules bombard the particle rapidly from all directions. Now, what is the result then? Let us consider the forces acting on the particle. Obviously, one is frictional force, because your solvent would be having a certain viscosity, it would give rise to a certain friction, right, and this we have seen before. So, here xi is the friction coefficient and v is the particle velocity. Now, that is one. Now, that is one. And what is the other force we just talked about? The other force we talked about is a random force, f of t. It is a time dependent random force f of t, but remember it is fully random. Okay, it has no specific bias with regards to any direction. That means it can hit and move if it has to, or it can hit in any direction or try to move the molecule in any direction. So, this fluctuates rapidly as a function of time, and this is the force which represents Brownian motion. Okay. So, what you can understand now is Langevin, what he tried to do was he was trying to model a molecule experiencing Brownian motion, taking into account friction too, because if that molecule is inside a solvent, it would also experience friction along with the fluctuating random force. Okay. So, then what he said was, see, this is easily understood. He took help of Newton's laws. What is dV by dt? What is dV by dt? Acceleration, right? Dx by dt is what? velocity, and then it is the double derivative of that, essentially dv by dt, it is acceleration. So, m times acceleration is what? Force. Good. So, then if this is having force units, the other two components or whatever I have on the other side of the equation should also be having force units. The first one is f of t, right, which is a random force, right. Now, remember, whenever your random force is, so if this is a molecule, the random force is in this direction, but if it is trying to move in this direction, what would friction do? It would try to oppose, because that is what friction does. And that is why you see, if the f of t is positive, then this friction coefficient times v, which is the friction force, is essentially negative. Okay. So, now this is very simple, right. I have a molecule inside, I have taken into consideration what? One is a randomly fluctuating force and the other one is just the friction force, and this is what my equation becomes. Now, what you can say is, well, obviously you can understand this is a very simple picture. You can say that I can be having an electric field coming in. So, what will happen in that case? I would be having the force of due to electric field being added to this equation, that is what it is. So, any other force which comes in, because this is my most general equation and I have taken only two forces into consideration, one being the random force and the other one is what? The friction force. So, any other force which might be applicable on the molecule can be taken care of by including in this equation, and then you can apply some steady state and then try to solve it. Okay. But this is one of the most general equations of a particle exhibiting Brownian motion, and this is something please pay attention to, please always keep in mind. This is the Langevin equation, okay, and it leads to very, very interesting facts. Okay. Now, what is the random force? The random force f of t, it is random, that means it is randomly oriented. Now, think about this, the number of forces or the number of force applications I will be having in positive direction would be equal to the number of forces I will be having in the negative direction. So, what will happen if I take the average of f of t? It would be 0, and that is essentially what it shows. So, you can see that the random force is always fluctuating around this blue line, right. This random force, which is a red, is always fluctuating around this blue line, and the blue line is your 0 line. Okay. So, if we take f of t, the average, then it essentially is 0, right, and it makes sense, right, because it is a random force. So, each and every direction is equally probable. Okay. Now, we will try to introduce a concept referred to as a correlation function. Suppose I have a force, a certain force or something, not even a force, something which is time dependent, okay, a certain property. Now, this property can be position, this property can be velocity, this property can be force or something else you might think of, and let that be represented as A. Then what we say is A of t is changing randomly, that means A of t now is fluctuating as a function of time, okay, that is what it shows, it is just fluctuating as a function of time. Again, there is no specific direction. Now, what happens is, think about this, for two measurements taken at times t1 and t2 that are very close to each other, that means I take a measurement at time t1, a t1, and instantly I take a measurement at time t2. Now, these two are very close, is not it? If these two are very close, then these two values would be very similar to each other, is not it, because you took it at time t1 and you took it at time t2, where t2 is very, very close to t1, only it does not is not equal to t1, but it is very close to t1. So, if it is very close to t1, that means this value and this value is almost the same, if not the same. Okay. So, number one. So, what we say is these two values are correlated with each other, right. Then when will this correlation not be there? If two measurement times t1 and t2, where t2 is far moved from t1, if far moved from t1, right, then the relationship between a t1 and a t2 is no longer there, that means this is called uncorrelated, right. Now, this is what the statement of correlation and uncorrelation, non-correlation is, right. What do we exactly mean by this? What we mean this is very simple. You think about this, your particle is exhibiting, or your particle which is mass m is inside the solvent, the solvent molecule is hitting it randomly, right. Now, suppose the particle starts with an initial, the particle of mass m starts with an initial velocity, say v, at t certain v, say t is equal to 0, that is my 0 time, that is the time I make the first measurement, say t is equal to 0. Now, after this, because it is being hit randomly by so many surrounding solvent molecules, what will happen is this V0 will not be same. What will it depend upon? It will depend upon the number of collisions, the number of random collisions I might say from the solvent molecules. And when do you increase the number of random collisions? That means with time, if you give it enough time, the number of random collisions would be a lot more. So, if the time is very short, that means if T2 is very close to T1, the number of random collisions is what? Very small. So, hence that value of A T2 is very close to the value of T1, or in that sense it is correlated. Now that means V at T1 or V at T1 is equal to 0 is very close to V at T2, where T2 is greater than T0 or T is equal to 0 by a small amount. However, if T2 is say infinity, that is moved largely from T is equal to 0, then what will happen? Because of the many random collisions, what has happened? The particle has actually forgotten what initial velocity started with, because you have had so many random collisions, and these collisions again are random. So, do you think if my T2 is really large as compared to T1, where T1 is equal to 0 in our case, would there be any correlation between these two? No, right? That is where we say it is non-correlated, not correlated or uncorrelated. Okay? So, this is essentially what a correlation function tells. What a correlation function tells is, if I start with a certain property, as a function of time, what happens to the correlation function, and what would happen? As a function of time, the correlation would start from a very high value, right, and then what would happen? It would slowly go down, because the correlation would become uncorrelated. So, that means there would be a decay in your correlation function. This is referred to as a correlation decay, and that is what the third point is. The extent of correlation should then progressively move towards lower values as a function of time, and this is referred to as correlation decay. Okay. If you would look at any dynamics, you would see this correlation function has a huge presence. I am not sure whether you have come across this when you were doing statistical mechanics. There was something known as fluctuation dissipation theorem and all these things. I am not sure whether you have done that or to what extent you have done that, but this correlation function has a huge place in physical chemistry. It is exactly the heart of physical chemistry, especially Brownian motion, right? And you can actually figure out by the correlation time, in what time would an initial property of a molecule become non-correlated. Simply put, can I say this? Can I say that this correlation function is essentially a memory function? What do I mean by memory function? Memory function is, if the particle starts with a velocity V0 at t is equal to 0, that is my initial time, then what is the time it will take to lose its initial memory, which had the information that its velocity was what? V0. Is it not? Because V0 and T2, where T2 is much greater than t is equal to, or T1 is equal to 0, they are not correlated. And they are not correlated. Why? Because it has just lost its memory of what initial velocity it started with. So, this is essentially something known as a memory function. So, it does not keep in mind. It's, let us take a very practical example, right. Now, first of all, if you consider my memory, I am getting old, so my memory is already going down, right. Second, one of you starts with asking me a question, right. Now, then we have so many people out here, everyone else also starts asking me a question related to that. But maybe if it is related, it is not a problem, but suppose the questions so happen that they are not really correlated with each other or not really related. So, the first question you ask me and the last question I answer might not actually be related, right. So, that means I have lost the memory from what I started with and from where we ended. But if you talk about, say, if this was the, say, the 20th question, and if this was the, say, the second question, then the second question and first question at least would be much more related than the 20th question and the first question. So, that is essentially what a memory function is. So, how fast you lose your memory of what you started with, and that is a correlation decay. Clear? Okay. So, this is just a schematic representation of your correlation function. What does it say? So, you can say, as I was saying, t is equal to 0, say I have this property A at t0, right. If I have this probability A at t0, then what is T correlation? T correlation is the time that is elapsed since I have made the first measurement, or since I have made whatever that A is at t0. So, you can see this T correlation, the blue one is your T correlation, that what is happening to the blue one? The blue one is slowly shifted with respect to time. Okay. So, let us think about this. If you think about this maximum, when T correlation was 0, what would have happened to the blue curve? The blue curve would exactly superimpose on the black curve, because T correlation is 0, right. And what is T correlation here? T correlation is the shift I have in terms of what? In terms of the blue curve and the black curve, right. Now, if this is how I define my correlation function, what will happen? You can see, if initially this was on top, then these two would absolutely be correlated. Now, what is happening is this one is slowly moving out, this one is slowly moving out. Because it is moving out, as compared to this one, now say here the value of this one is this, the blue curve, is not it. At the same point, at the same time t, the blue curve has moved. So, this value has already come down to this, but this black curve is still there, because this is what my initial was. Now, think about this. What will happen is, if I take the product of A t0 times A t0 plus T correlation, don't you see that because this T correlation is shifting like this, the product of A t naught times A t naught plus T correlation is decreasing? Do you see that or not? See it. So, let me see whether I can do it. So, this is what I started with, right. This was one curve, and then this was the dotted curve, both are at t naught. Okay. Now, what has happened is my t naught is still here, because that is what I started with. Now, what I have done is I have moved it by T correlation. So, initially what was happened? Initially it was A t naught times A t naught, right, which is both here. Now, what is happening? This is this, this is this. So, this is A t naught times A t naught plus T correlation. Okay. So, what has happened to this now? The product is already decreased, is not it. So, you allow it more time, what will happen? This dotted curve will move fully out of the domain of the black curve or the solid curve, and hence finally you would lose all correlation. Essentially what you are seeing is a correlation decay. Okay. That is how you define a correlation decay, right. So, then what is the time correlation function? Obviously, correlation is a function of time here. So, a time correlation function describes how long a given property of a system persists until it is averaged out by microscopic motions and interactions with its surroundings. Now, that is what we discussed at length right now. So, then what is x? So, this is referred to your position correlation. What is f? Force, then we say force correlation. And what is f? V? Velocity, and we say velocity correlation. Okay. So, this is the one we are now going to look at in some detail. So, we are talking about the velocity correlation, and we are trying to figure out whether we have an expression which would tell us, or which would tell me how long it would take for the initial velocity, the memory of the initial velocity to be lost or to decay. That is what we are going to look at. Okay. So, let us look at this. Look at the velocity correlation function. We will start with the Langevin equation, m dv dt is equal to f of t minus v. Let this be 1, and this was your Langevin equation. See, this equation was absolutely logical. Langevin did not have to derive it, he did it. Any one of us could have, but this is where this is where could have and did have or did do comes in. I could have, but he actually did it. Okay. Now, think about this. I am considering this velocity correlation, which is V 0 V of t. I am considering this velocity correlation function. If t is very close to 0, which is this 0. So, 0 means my 0 time, right. It is like what I had for t naught and t naught plus t correlated. What I am saying is t naught is equal to 0, then any other time t correlation is essentially t for me, right. So, if t is very close to 0, then what about v of t? It would be almost tending to what? V 0, excellent. Okay. So, then what is the maximum value of this ensemble average? Then I can immediately write, then for this V naught V of t is equal to V naught V of or V naught V 0 V 0 is equal to V square 0, right. So, that means at time t very close to 0, from when you have started looking at V 0, which is t is equal to 0, they are absolutely correlated. Okay. Now, what will happen? What will happen if t is much greater than 0? If t is much greater than 0 now, as we just discussed, then V of t and V of 0 will not be correlated. V of t and V of 0 will not be correlated, right. Under that condition, can I write this? Can I write this V of 0 times V of t, because these are not correlated and you know these brackets resemble the ensemble average, then can I write this to be equal to V naught times V of t? See, these are not correlated, right. So, V of t is absolutely independent of V naught, because you have lost all correlation, is not it. So, this is what you do when you do like particle in a box in 2 dimensions, 3 dimensions or whatever dimensions. What do? You say that my motion in the x direction is totally uncoupled from motion in the y direction, then what happens to the wave function? It is a product of the wave functions. This is essentially what you are seeing out here. That means you are now being able to separate the motions. Why? Because there is no correlation between the initial motion and the final motion, or in this case the initial velocity and the final velocity. That is what you are essentially doing, right. So, this I can write as V squared, and what is V? V is my average velocity. Okay. What is V? V is my average velocity. That means my velocity is fluctuating, right, and then I have an average velocity over a function of time, and this is essentially what it is. This is for when all your correlation is lost. So, you can understand one thing. That the V starts from V naught V 0 squared, that was the maximum, and then it decays to what? Its ensemble fluctuating average, which is V squared. Okay. Now, these two quantities, not exactly these two quantities, but quantities like this again you have come across in quantum mechanics. What is it? Do you remember? How was your variance? Written as in quantum mechanics? Remember sigma a squared or sigma a, the uncertainty? What was it? Wasn't it average expectation of a squared minus expectation of a whole squared, right? Now, what was that? That was the uncertainty, isn't it? So, you are seeing a very similar thing out here. The first one is expectation or average of V squared, expectation is your average. The next one is what? Expectation average of V whole squared. Okay. So, then the correlation time, I would define the correlation time is as that time or by which the initial memory of V naught is being lost. Okay. I will not write this. So, what I am saying is again, so the correlation time is defined as that time beyond which the memory about the initial velocity started with at t is equal to 0, which is V 0, is lost, and that is something we are trying to derive here, the correlation time. Again you are losing the memory V0, and this, what is the time you take to lose this correlation, to lose this memory, is a correlation time. Okay. So, that means what we would now do is try to derive your velocity correlation time. Now, what we do is we again start with, as I said, the Langevin equation times V. Okay. Now, what I do is, this was equation number 1, I am writing it again. Now, what I do is multiply throughout by not V naught, just write V 0, because that is what I said, not V naught, just write V 0. Okay. Now, if I have that, then I can write m V 0 dV dt is equal to V 0 f of t minus psi V 0 V. This is equation 2. Now, what you do is you take the ensemble average. You take the ensemble average. So, what do you mean what do you mean we take the ensemble average? That means we just introduce these brackets throughout the whole equation, right, sweeping through the whole equation. And if I do that, can I write this? Can I write this? Can I write m d of dt, okay, ensemble average V 0 V of t, this is my left hand side of the equation, is equal to V 0 sorry, okay, not sorry, just put this in brackets, I am just always forgetting this. This is actually 0, okay, this is the same as V 0, okay, sorry, it does not matter, but anyway we stick to what we do. F of t minus xi, then V 0 V of t, and this would be equation number 3. This would be equation number 3. No problem, right? Why can I do that? I can do that because V 0 is what? A constant or not? It is a constant. I know the initial velocity of the particle, it is a constant value, right. So, we just put it in the equation. Now, look at this. I can write that V f of t, this term, is equal to V 0 times f of t. What is the assumption? The assumption is that f of t, the fluctuating force, has no correlation with the initial velocity of the particle, and there should not be. Fluctuating force is coming from what? It is coming from the fluctuation of the solvent molecules, right, and that fluctuation has nothing to do with the initial velocity that the particle starts with. Okay. So, that means f of t is not correlated with V naught. Now, if that is the case, tell me this, what will happen to this? 0. Why? Why is it 0? Not V naught. What about this factor? What about f of t? F of t was 0, right? That is what we defined. This is my randomly fluctuating force, and when we take the ensemble average, that is 0, right? That is what we started with, remember, my random force. So, if f of t is equal to 0, then V 0 times f of t is essentially equal to 0. So, in essence, what have you done? In essence, what you have done is you have simplified the equation instantly, right? The moment you took the ensemble average, you know that the f of t is a fluctuating force, it should go to 0. So, your differential equation is left with only 2 terms, right? You simplified the equation. So, then based on this, what we write is m d of dt v of 0 times v of t is equal to minus xi v of 0 times v of t, and so this be equation 4. So, can we solve this equation now or not? We can easily, right. So, what we can do is we have d v 0 v of t. Okay. So, this one comes down now, v 0 v of t is equal to minus xi by m d of t. We integrate both sides, and what do we integrate between? What would be our integration limits? 0 to t, excellent. So, we go from 0 to t, we go from 0 to t. Now, at t tends to 0, what is v of t? v 0, because t is equal to 0 and the particle has an initial velocity v 0. So, if I do this integration, what do I come up with? This is what I come up with. I come up with v naught v of t is equal to, tell me what is the first factor, is not it? So, this is what, if you take ensemble of v 0 by v t to be x, this is dx over x. What is dx over x? dln x. So, this it would be ln what? ln v 0 times v of t over v 0 times v 0, which is v square 0, right. Then you separate it, raise it to the power e. So, it comes v 0 times v of t is equal to v square 0. Now, this is exponential, what do you have? Minus times t. Isn't it? Because this one is essentially what? T between the limits, that is what it is. So, what do you now see? What you see is that your velocity correlation function is having an exponential dependence on what? T, based on a certain constant which is xi by m. What is xi? Friction coefficient. What is m? Mass of the particle, right. Now, tell me this, I am sure you guys know, if you have anything in the exponent, then that should be dimensionless, that should not be having any units if you have anything in the exponent, same for log. If you do that, then if the exponent has to be dimensionless, that means if exponent minus xi by m t, if this is dimensionless, how can it be dimensionless? You know t has a function of time, right, it is either second, minute, hours, whatever, does not matter. So, if t is time, then the coefficient should be inverse of t, right. So, that means if t is time, then xi by m should be what? Time inverse. If xi by m is time inverse, then from here what can I write? M by xi is time, is not it? M by xi is time, because there is the inverse of time inverse. So, essentially see now, then the equation becomes, I can write v 0 v of t is equal to v squared e to the power minus t by, say, I say tau, where tau is equal to m by xi, where tau is equal to m by xi, and this is your correlation time, and this is your correlation time. Okay. Hey, remember this, when you did a first order kinetics, what was it? A was equal to concentration of A was equal to concentration of A naught times e to the power minus kT, right. What did that exponent signify? That exponent signify the time it takes to decay, right, to a certain value. That is how we would find. What is the unit of k you guys got? It was always second inverse. Why? The reason was it was e to the minus kT, right. So, t was time. Remember, my exponent has to be what? Dimensionless. So, k better be what? Second inverse, right. So, that is how you get it. Even without deriving, even without just going through it, you can just look at it and see, okay, yeah, k has to be having the dimensions of inverse of time, right. So, here this tau is the correlation time. So, what I do is, if I draw it, so for example, if I am drawing the function velocity correlation function v of t, right. So, this is what your y axis is, and if this is t time, then my correlation function will be exponentially decaying, right. Where will it start from? That means at t is equal to 0, what is the value of the correlation function? Very good. So, at t is equal to 0, my correlation function is v square 0. Now, it decays as a function of time. What parameter defines its decay? Tau. That is why tau is the correlation time, right. So, what it says is, if I know my tau correlation, what does this mean? Tau correlation means that if t is less than tau correlation, if I write this one as correlation, okay. If t is less than tau correlation, that means for any time which is less than tau correlation, my velocities would be what? Correlated, because t is less than tau correlation, isn't it? That means v 0 and v of t have correlation. That means it still retains some memory of its initial condition, starting point. However, if t is greater than tau correlation, what will happen? There is absolutely no correlation, it is totally uncorrelated now. So, v is, so that means if t is greater than tau correlation, it means velocities are uncorrelated, okay. So, this is the significance of correlation time, and you can understand, if you are talking about velocity, any particle would be having a certain velocity, right. Any particle would be having a position too, any particle would be having some force too, as we said, position correlation, velocity correlation, force correlation. So, that means these correlations would be decaying as a function of time according to this tau correlation. So, that means if you start with a certain value of position or certain information on velocity, you would know that if I know my tau correlation, that means you exactly know if the time elapsed since my t is equal to 0 is tau correlation, then I am at the borderline, and that is the last point at which there is some correlation between initial velocity and your v of t. Beyond that, you have lost all correlation, okay, and that is how you look into it. So, what we will do is we will stop here for today, but what we will do is next class go a little deeper into it. I will tell you the relation between this time average and diffusion coefficient, and remember, when you did Brownian motion of gas particles, which was a kinetic theory, you always talked about root mean square, speed and all these things. So, that means a very important parameter in any dynamics, is referred to as something known as like mean square displacement, okay, or mean square speed. So, what we will do is next class we will derive an expression for mean square displacement of a particle exhibiting Brownian motion. It is Brownian motion because its force acting on it is subject to what? A random fluctuation from the soluble molecules, and you will see, you will actually get a very interesting result. You will see that all whatever we have talked about are so very much